Okay, ready to go? Okay, guys, I need a little bit of help today, unfortunately. So maybe one of you has a Wacom tablet and can share a pen with me. I accidentally left my pen at home. Yeah, one. Okay, cool. Yeah, I have a spare pen for my laptop, but it turns out I didn't use it for so long that it ran out of battery, so it doesn't work. But thank you. I hope it will. Okay. So people on Zoom can hear me, right? I hope. And like there's a bunch of people on Zoom now. I appreciate actually that so many. And this works. Well, amazing pen works. The person who has a pen is in the first row, and yeah, that's also very cool. Okay, let's go. So this is what we were doing last time, right? So we ended talking about procedure invocations, right? So we kind of have a high level picture. Actually, we actually have the whole picture now. So remember this jump and link instruction, which allows you to save the return address in the return address register, and then we do all this stuff, and then we return through a register with a jump via register instruction. And I wanted to just make a couple of clarifications, which I wasn't sure on the last time. Remember, this is remember this convention about the registers which are preserved by the caller and the callee, right? So, for example, if you call a function foo, inside the function, this foo is free to override temporary registers T0, T9, right? So it can just simply do an addition on putting result in T0, and it doesn't have to restore the T0 to the original value before foo was invoked, right? And that was there. I was confident about it. What I wasn't confident about it is about those registers, the argument registers A0 through A3. Remember, we pass arguments in those registers, and I wasn't sure whether you can touch them or not. And apparently you can. So, like according to the book, you don't have to preserve them. So you are free to do something like putting a result inside A0 as well without saving and restoring it, right? So this is what I was confused about, right? And obviously the return value registers are for you, for the function to return the result, right? So you're expected to put the result in them, and I guess you can use them as well in any arithmetic operations and freely inside your function, right? So do whatever you want. So you're free to do something like add into V0 and add into V1 as well, as long as even if though you don't plan on returning anything through V1, maybe you just still it's a free register for you. You can do whatever you want, right? It's allowed by the calling convention, right? So what you have to preserve is those registers S0 through S7. So because the caller expects them to be unchanged, you have to preserve the stack pointer to the original value, right, like it was before the function invocation, and you have to preserve the return address, right? And that's roughly like this argument about the stack. So supposedly you're not supposed to touch the memory, like if this is the stack and it grows down, and this is the value of the stack pointer before the foo was invoked. So when foo started running, the stack started growing downwards, and like foo operates supposedly on this area of the stack, right? However, I personally like if you pass a pointer inside foo, which points somewhere on this stack, you're fine to modify it. So that's okay. But technically, you typically just operate on this area of the stack, right? So this is yours, and you shouldn't touch the one which belongs to your caller, right? So is this last kind of clarification about the calling convention clear to you, or are there any questions? Okay, go ahead.
So this example you drew at the bottom, that's like a side effect function where it like changes something that it doesn't return.
Well, side effect functions, yeah, there are pure functions and non-pure. And in our languages, in the languages which you know, typically functions are allowed to change anything, right? And so they're not pure. So it's just a function that typically you can say that the pointer should point to somewhere on a heap, right? But there is no restriction really. Like if the variable is alive and is really alive, you can pass a pointer like that. And I don't know like how much you know at this point about the pointers, how well you understand them. In like languages like Python, they conceal all about pointers, so you don't know much about them. In C++, C++ has a lot of language boilerplate, which also helps you to forget about pointers if you don't want to deal with them. So I don't want to go strictly into the details. I just like, the reason I started talking about it is that I kind of disagree with the book on this, or let's say partially agree. So I wouldn't, if I were you, I wouldn't like spend a lot of time trying to like argue about it.
Technically, you can modify them.
Technically, and C would be perfectly fine with you doing this. And I don't know why the book says that. Okay, you shouldn't change anything above the stack pointer. So technically, you can if it's passed as through a pointer, right? But it's uncommon. And of course, just last time someone was asking what happens if you the stack runs into the heap or something like that. So along the same lines, there are cases when this calling convention is violated, and it's a little bit, it's towards advanced techniques. But if you've heard words like asynchronous threads, they exist, I think, in Rust as a standard, but you can build them in C as well, or green threads. You know, when you build those threading libraries, then you start abusing the stack, but you have to be clear about what you're doing. So language runtimes do that. They don't always follow those conventions, right? But typically they say that normal language code should not do anything like crazy. Okay, so this is one clarification which I wanted to make, and another was about this shift by 1 and multiply by 2. For that I will switch to like a slightly better whiteboard, this one, where I can write better numbers. So like the question is, I keep saying that if you want to multiply a number, A, for example, goodness, that I have to restart. They didn't detect the pan. Let me just quickly restart this. Okay, we're good. So I kind of say that if you have a number A and you shift it by, for example, 1, it's the same as multiplying A by 2, right? And like I kind of assume that it goes without saying, but it's also very easy to explain. So right, imagine, how is that, what is this really number? What is this number A? Imagine we represent it as a binary number, right? So it's a bunch of bits. So, and typically in those bits, you would have something like 0, 1, 0, 0, 1, 1, for example, and 0 here, right? And the number, if we name those bits, it's like bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, and bit 6. Really the number is actually, it's 2 to the power 0 multiplied by the value of b0 plus 2 to the power 1 multiplied by b1 plus 2 to the power 2 multiplied by b2, and so on, right? Agree with this? So in our specific example, it will be A will be 0 multiplied by, it's like 2 to the power 0 is always 1, right? multiply by 0 because this is 0 here, then plus 2 multiply by 1 plus whatever 4 multiply by 0 plus 8 multiply by 0 plus 16 multiply by 1 plus 32 multiply by 1 plus 64 multiply by 0, right? Agree with this? And so like if we think about this number, it's like essentially this is 0, this is 1, so it's 2 plus this is 0, this is 0 plus 16 plus 32, what is it, 48 plus 2, so 50, agree? So this number is 50. And then what happens if you multiplying by 2? So multiplication by 2 effectively, if you multiply this number, if it's a multiplied by 2, then when you're multiplying by 2, it's 2 multiplied by this giant expression here, right? So 2 to the power 0 by b0 plus 2 to the power 1 by b1 plus and so on to 2 to the power whatever. Which one is that? 0, 1, 2, 3, 4, 5, 6. 2 to the power 6 by b6, right? And if you put the 2 inside, so what happens, you remember how powers work, so it will become 2 to the power 1 multiplied by b0 plus 2 to the power 2 multiplied by b1 plus 2 to the power 3 multiplied by b2 plus up to this number 2 to the power 7 multiplied by b6, right? Agree with this? So because we just added the power, but this is effectively the shift, because remember here we have b0 with the 0 power, and now we're having b0 with the 1 power. So effectively it's the same as writing the same number as effectively as just shifted. So essentially, if my b0 used to be here, now this one is 0, just because 2 to the power 0 is now multiplied by 0, right? It just doesn't exist here. And this b0 becomes here in the first position. b1 becomes here in the second position. b2 becomes, like, occupies and so on, right? Got it? So this is why this is effectively, it's the same as a shift. Is that clear? So this is how the math behind it works. It's just, and if instead of 2 we're using the base of 10, the same trick works with tens. When you multiply by 10 in a decimal system, right, it's just essentially shifting by 1. So is this one clear? And by extension, if you look at this representation, you will agree that I wasn't sure whether you can multiply negative numbers by shifting. Yeah, you can. So in the same manner, right? Okay, this is good. So now we understand why shift by 1 is multiplied by 2, right? Any questions about it? Good. Okay. No, maybe it was just too exhaustive. I agree, but just wanted to make sure that we're on the same page here. Okay. So now our topic for today is actually kind of quickly finish the just bits and pieces of the assembly, and then talk about program linking and loading. And program linking and loading is a little bit of an involved topic. So the book only covers it in some shallow manner, and I will not spend a lot of time on this. So just give you an overview. And if you want to understand in details, you have to take the operating system class, in which, I mean, in my class, I go in details, and at the homework assignment, you actually build a loader. So you will have to like load stuff in memory, and we go into the details how the operating system loads the program in memory. My class is again recorded and open, so if you really care about it right now, you can watch those 2 lectures. And right before that, linking and loading, I talk about x86 assembly. So you're welcome to essentially which again, by knowing MIPS assembly, understanding x86 is not a big deal. So you kind of well prepared for that. Okay, so strings. So strings are a special representation for character data. Essentially, the idea is that you frequently represent characters, and there is a special convention which allows those graphical devices to actually draw something on the screen. So because when you want to print a letter like A, for example, and something like these shapes of pixels appears on the screen, right? In practice, you just represent it as a number, and I don't remember exactly the number, but let's say 32, for example, right? So this is how you keep the letter A in memory. So it's just 1 byte, which says number 32, and there is a special table which essentially converts, like it's a convention. It just says, okay, that 32 is a character. Like here I have exact numbers. So like capital 8 is 81, lowercase a is 113, 30 is not even in this table, but it does represent some character, maybe like a line like that, or maybe an angle like this, right? So there was a question. Let me just quickly stop here, take it. Am I what? Have I posted the slides? I haven't. So do you read them right now? Do you need them right now? Let me just do it. Just give me a sec. I forgot. I meant to do that when I was, and then I understood that I forgot my pen, and I have to concentrate on the pen business. Do we have a recording for the lecture? We do. Oh, so you believe that I'm not recording? Oh, that I don't know, but theoretically I put it online. I usually try to do that right away. So if I forgot, that's theoretically possible, but please check or just ping me on Discord or on Piazza and I will do it. Okay, so where are we here? Just for everyone to understand. Sorry. So if you reload the web page, it will be the same URL as last time. So it's we can get it right. Sorry about it. That doesn't work. Why is that? Slideshow, come on. Okay, get back to the ASCII character. So this table is called ASCII table. So, and there is a, I don't remember what the acronym stands for, but this is something like American Association for something, right? But essentially it's an idea that you can represent every letter as a numerical value, keep it in memory like that. But when it comes to drawing it, the hardware which is aware about this ASCII set, right? It will know that if you're transferring the number, whatever was B, I forgot already. So B, capital B was 82. So when it comes to like 80, like putting 82 on the screen, this hardware will essentially draw it as a collection of these like dots. And you can typically, when you pass, you can also pass a color along with the number to the hardware interface, and that it will choose a bigger color. And so, for example, if we are like, if you look at my shell, this is kind of like the history of it is that originally shells were just printers, right? So that's why this like things like ls make sense. So like imagine you have just a printer which has a roll of paper and just I type ls, I don't see what I'm typing, and then it prints out the files like this one string of of this one. So this was the very first terminal, right? And then later on, people came up with cathode ray tube terminals, which were primitive screens, right? And then they were essentially, those screens were able, for each letter, they were able to kind of like draw this on the screen. And there was a notion of font, but not as advanced as we have right now. So this is all obviously goes to the graphical interface. I can switch to a real ASCII string, but then I will lose screen sharing, right? So this is convenient. And so typically, I mean, the reason, why am I talking about it? So you probably have seen, like when we want to do something like print hello world, there will be something like hello world in memory, right? And you also put this magical end of line character to essentially say, okay, when you stop printing this screen, please, the terminal like will switch to the next line on the screen, right? And this is how it will be represented in memory. So essentially for H, you will, like typically assembler or a compiler, depending on what you're using, but let's assume you're using assembler. And next week, we're gonna take a look at examples of real programs which we can program in assembly. So we will put this in a data section. Remember, I kept saying that there will be a data section, and there is something like a string directive in assembly. And this string allows you to essentially say, well, allocate space for this string. And like, since you wanna, you can type it by hand, by number. So essentially put, instead of H, you can put something like 88, right, in memory. But it's cumbersome. So for a human, it's much easier to say, like, type the string and assembler will encode it automatically, right? And in memory, it will be as a collection of bytes. So that will be 1 byte, not a word. Remember, word is 4 bytes. So it will be just a single byte. Then E will be 117, right? And so on. 1 byte allows you to represent numbers from 0 to 255, right? So a total of 256 numbers, right? Get it? And the question is, how do you mark the end of the string? So who knows? Who can tell me? What are the possible ways to do this?
You could use a 0 byte, like this also.
So one typical representation is that at the very end here is you put a 0 here. And then all the routines which manipulate strings, like count the string lengths or copy one string into another, they know that we're going to be going through this array until they reach 0, right? So this is a typical representation in a language like C. And like, again, in the assembly, which we're going to be using, it will be there as well. A better representation might contain an array in memory, or like a data structure, which might have a len here in the first field, and then just whatever the string data here, right? So it varies from language to language, but those are the 2 most populars. And later on, when we started running out of characters, because if you have an exotic language like Ukrainian, for example, right? So you can either overload this ASCII table and say, look, some positions which are not used by English alphabet will be used by Ukrainian alphabet, and there will be a letter like I or something like that. So like, or I with double dots, right? But then, you know, like Asian languages and stuff like that, even more symbols. And so people came up with a new standard, which is called Unicode, which instead of a 1 byte uses 2 bytes per character, right? And those can keep in memory much wider alphabets. And again, like the string is represented as a collection of 2 byte values with some kind of a delimiter, which tells you that that's the end of it. But really, then the hardware or the graphical user interface just like says, okay, look, I know that this is some specific character in this alphabet, and just draws it on a screen like that, right? Any questions about it?
You said Unicode is 2 bytes, or is it 4 bytes?
Unicode, I think the typical representation is 2 bytes. However, the slide, and this is what the book was saying. So maybe there might be, it's a 32-bit character set, which is 8 bytes. When I was reading the book, like yesterday, essentially, it was saying 16. So let me come back on this. I'm pretty sure that there are multiple Unicode standards like UTF-8, UTF-16, and maybe UTF-8 allows you to actually encode in 1 byte, and 16 means 2 bytes, and maybe there is a 32-bit encoding. So should admit, not an expert in Unicode. So since I'm typically build operating systems, we're lucky. We're one lucky people who don't have to deal with Unicode. Everything is just as key altogether. Yeah. English what?
Just because of English.
No, just because it's much easier to build device drivers which output something in a key. You don't have to like build layers of software which deal with Unicode, and it's enough to print characters during the boot, right?
Okay.
And yeah, and everything is in English, so we are fine. Yeah. Okay, cool. So you got the point. However, so this hardware, MIPS hardware, has specific support for this, right? Because as I was mentioning, ASCII is just 1 byte. And so up until now, we were talking about load instructions and store instructions, which load the whole 4-byte value, right? And so the hardware provides a couple of things. So they have a load byte, which actually like loads just 1 byte. And signed extends, if you do into the register, go load into the register, it will sign extend the register. So it will just load the lowest, if you have, 4 bytes, it will load this lowest byte and then sign and extend here with, for example, zeros if it's unsigned, load byte unsigned, or with whatever it is, if it's a signed value or unsigned value with ones, right? And similarly, it has a store byte, which allows you to store a specific byte, just 1 byte, right? So this one stores, I guess, just the rightmost, so this byte, right?
So these are MIPS operations for strings.
These are MIPS, right? So this is implemented by the machine and supported by the MIPS assembler. So just specifically to simplify operations on strings. Otherwise, you can deal with it. You can load the whole world and then word and then just do a shift operation and mask out what you don't need, right? So I assume, but it's doable as well. But they came up with saying that this is so frequent that we will rather support it. And so, for example, just again, let's take a flashback into functions and assembly, right? So let's implement a naive version of a string copy procedure, which takes 2 pointers to strings. So they, like in C, we can encode them as arrays and copies Y into X. So the C code will be something like you have a counter I, which you initialize with 0, and then you go through the array until the element of the array is not 0, right? This magical, remember, the string is represented with a collection of bytes, and then the last byte is a magical byte 0, right? And this is how you, in C, you say that this is the character 0, not the character, but actually value 0, right? And this is an assignment. I mean, I'm not an advocate of writing C code like that, which has assignment here, and at the same time a check for equality, right? I would say it's about that taste, but we can do it. We can do it this way, and then increment the counter here by 1, right? So you're going through the array. So addresses of X and Y are in our argument registers A0 and A1, and I inside S0. Again, I wouldn't argue that it should be inside S0. I would be perfectly fine to put it in T0 just to say that we will be using a temporary register instead, right? But it's whatever, just one way to write this in assembly, right? So again, we adjust the stack for 1 item, right? What is this 1 item? Who can tell me? I, yeah, exactly. Since we said that I will be inside S0, we'll save it on the stack in the next line. So essentially, this one uses the stack pointer and saves as 0 onto the stack, right? Then remember, there is no way to like put a 0 into a register. So what the trick which they do is essentially they use this add instruction, which uses this magical 0 register which adds 0 to 0 and puts it back into S0, right? So that's one way to initialize I with 0. So,
حمام نفس
can someone on Zoom?
نفس حمامات الجامعة.
Thank you.
الحمام
Ali, can you I can probably, okay, maybe. And then what you're going to be doing is that you will be put the address. Remember, we have A0 contains which argument? A0 contains X, and A1 contains Y, right? So what you put in here is address of, you take a counter as 0, add it to A1, put it into a temporary register T0, load from, put it into T1, load it from the T1 into T2, and you're using this instruction, which is load byte, because you're just simply using 1 byte here. You then, again, using A1, which contains the base of X plus a running counter as 0. And remember, we don't have to multiply here by 4. So we typically we're going through arrays in the increments of 4, but since it's a byte, we'll just, we'll increment by 1 byte, because in memory, this X starts at some address. Let's say we can say 1000, for example. So the 0 elements start at 1000, but then the first element is at byte 1001, right? So you don't have to do any multiplication here. So it simplifies your code, right? So, and here you say store byte, remember T3 contains the index itself, right? And you're saving T2, which contains the byte which you loaded from a string. Then you check for equality, like if T2 suddenly is 0, you jump to, you branch to L2. L2 says that's the end of it. We will restore S0, which is here on the stack, back into S0. Deallocate the space which we allocated here, right? And return from a procedure, right? So since it was a leaf procedure and it doesn't invoke any other procedures, we don't have to save the old value of the array register, right? So this optimization allows you to essentially save one stack operation, right? And if you don't branch here, then you add 1 to the running counter and jump back to L1, right? So again, if I ask you to write it as a homework, which I haven't assigned yet, that's kind of the flavor. So if you have issues with writing those procedures in assembly, so just come back to those examples there. Almost everything what we will assign will be along the same lines. So just a simple thing which was a loop, which has a couple of counters. Any questions about this string copy? Yeah, good. Load byte unsigned. You say, wow, it's easier for me to operate on unsigned numbers here. There was another question over there. You could, yep. Sorry. Asking, do I have to deal with running counter versus is that the question? Right. So you have S0. That's right. I have S0 and D1. Okay, that's a great question. Okay, let's come back to it. So what your classmate is asking, so in this line under the label, there is, let me clear everything here. So in this line, we're saying, hold on, we're first adding the running counter, which is inside S0, to the address of the Y array, right? And putting it into T0. And then we load byte using T1, this T1, which is here, plus 0, right? And what your classmate is asking, if I understand correctly, can you write an instruction which is something like LBU T2, place this addition here, so kind of like a running counter S0, and relative to A1, right? That's what you were asking for, right? So, okay, that's my question. Can we or can we not?
The offsets take register.
Exactly. So offsets don't take registers. Remember, I mean, and I mean, it's a great idea. I don't mind it. It complicates the implementation of the instruction set. Remember that those load operations, they are encoded as opcode, one register here, which was called target, or register target, RT, register source, although it's a destination, okay, 2 registers, and then an offset, right? If I remember correctly, that's the encoding for the load type instructions, right? So, and that's about it. They don't allow you to specify a 3rd register. And why is that? Why is that? That's a good question. I would assume, actually, I said that it will complicate the hardware, but when we actually get to building the hardware, we can come back and essentially we can ask ourselves a question, if we still remember, is it easy to build this instruction in hardware? And naively, I kind of assume that it's not that hard. I can be wrong though. Let's wait for it. For right now, this instruction set doesn't allow it. The question is like, is it just a historical mistake or is it a very sane design choice? Let's try to answer it. I don't know really the answer right now. There was another question, but it's good that you asked because yeah, it's not allowed. Anything else? Good. Okay, so I hope that at this point we kind of like become friends with assembly, right? So everyone can write procedures. And again, the beauty of it, it's so simple. It's just like literally 10 things you have to remember. And we'll come back in a second to the entire assembly table, just today actually, to kind of recap which instructions we remember, we know. There is a little bit of this support as well, which we didn't cover yet. So remember that all this immediate operations like add immediate and stuff like that, they allow you to load reasonably small constant, right? Because the whole instruction, if you take the whole instruction and encode the instruction, right? So if you have the instruction, there will be an opcode, like let's assume like 5 bits, and the maximum constant which you can fit here is only so many bits. So it's definitely less than 32, right? So which means that you cannot represent in one instruction, you cannot represent constants which are 32-bit numbers, right? So, and for that you say, okay, you might be puzzled. So is there a way to essentially load a 32-bit number into a register? And the answer is yes. So they provide this instruction, which is called load upper immediate, right? And what it does, if you have a register here and a constant 61, instead of being loaded in the lower bits of the register as 0, it will take upper 16 bits. And this is the constant 61, which instead of going here, like we usually do with all this add immediate, it goes into the upper bits. And this is how you can essentially create a 32-bit constant. You first load the upper 16 bits, and then you use an OR immediate to say, this is my lower 16 bits, this is the number 2304, and when you do an OR, obviously just this will be ORed with zeros, right? Agree? So that's the trick. Finally, like we still, remember I promised that there will be 3 types of encodings, like a register type, R type, I think it's called load type, and then the jump type, J type. So those jump instructions are encoded. And again, we talked a little bit about it. So there will be an opcode. I was wrong when I was saying 5 bits in the previous slide. So it's 6 bits for an opcode, 5 bits for a register. That's natural because you have 32 registers, remember. So 5 bits represent exactly numbers from 0 to 31. Another register and a constant, 16 bits, right? So an example of this instruction will be something like branch when equal, right? And you compare these two registers, source and target, and then if they are equal, you're gonna branch to a specific address, right? But you might ask a question, okay, there is only so much space, like it's kind of related to the previous discussion. So there is only so much space for the address to put there. So in specifically only 16 bits, right? So which means that if you want to branch anywhere in your program has to be very, very small. So 2 to the power 16. And what is this number? Is it 64? I would say it's 64 kilobytes, right? So it's a tiny program. I mean, I don't remember this power off the top of my hand, unfortunately, but it's a tiny program. Right now we write programs which are like megabyte, easily multiple megabytes, sometimes hundreds of megabytes because of loadable libraries. Most of the space actually goes to representing Unicode and stuff like that. Like literally the graphical stuff takes a lot of space. So what do you think can be like, what can be a trick to first extend the space, and second, like play a nicer trick, like so you can branch inside bigger programs. Let's imagine you have a program which is like 10 megabytes and it sits in memory. What? Yeah. Say again. Having point. Hold on. Having pointers. So that's tricky. So what do you mean a pointer?
It's like, you know, like just stack pointers. Like the files getting really big, have pointers throughout the files.
Right, but there might be something like a bit of truth in what you're suggesting. So let's hear a little bit more.
What if you just kept track of where all the labels are? So like where all your functions are, and then you could jump to like any function instead of any line.
To the beginning of a function, but you also have to, that supposedly can work, and you can say I can create a table which will contain locations of all functions, and then hardware will be instead of like using an address, it will go and pick an entry in this table, right? And you might have a specific register which points to the table. It probably works, but it kind of, again, if you like, part of the CS program is to teach you how to do good design, and it's kind of becomes a little bit complicated or ugly, if you like, right? So like we have to have this table around. You still don't know whether you will run out of space in the table, stuff like that, right? And plus you're wasting space on the table itself. Say again. Oh yeah, so that's the right answer. So what your again classmate suggests is to jump relative to where you currently are. There's a little bit of an interesting observation here, because most of your branch targets are nearby, and it's kind of intuitive because you say I write a function and typically I jump within a function. It's kind of absurd to jump out to another function, to some label which is somewhere else. It's like, you know, you will not pass a programming class, right? So, and that makes sense. So all the loops are inside the functions, and functions themselves are, it's a bad taste to write giant functions. They're reasonably small, like a couple of kilobytes at most, right? And so this observation is taken into account, and essentially this address is not really an absolute address in memory. Instead, it's relative to your current program counter, which is pointing to the current instruction, and you can either jump backwards by providing a negative number or jump forward by providing a positive number, right? However, they said, okay, but let's play another trick, because we know that all instructions are 4-byte long, right? So, and if you jump to the beginning of instruction and it's a 4-byte instruction, then the lowest 2 bits will always be 0, right? Of an address, right? If you jump to the instruction boundary. So they say, okay, why do I have to keep those bits 2 zeros here, right? We all already know that those 2 bits, those are zeros, right? So let's just forget about them and not store them, and just extend whatever the value here is. Like, let's say it's a value A, let's just put 2 zeros, or in other words, multiply by 4 this number, right? And then you will be just jumping. So it will allow you to effectively extend this address from 2 to the power 16 to the power 18, right? So it's a slightly wider range, but it's a clever observation, right? And the fact that you jumping relative to a program counter is also a clever way, because typically jumps are local. And I will show you in a second how to implement a non-local jump, right? So is this logic clear? Okay, go ahead.
There is something that handles
Right. So the question is there a mechanism which constrains you or like triggers an exception if you jump too far? No, there is no. Like essentially, no matter which number you put here, like 1, 1, 1, 1, 1, 1, 1, the max number, it will jump. Hardware will just jump. I mean, if it makes sense, if it's logically consistent with the flow of your program, it's okay. If it's inconsistent, that you screwed anyway, right? You're jumping somewhere, right? But the hardware will just blindly jump. There is no exception. Anything else? Any other questions about it? So let's think of how we can jump a little bit further, right? So this is a jump, which like non-conditional jump instruction. And this is this J-type encoding. It's a new encoding. It just has an opcode, again, the same 6 bits, but the rest is an address. And this guy is an absolute address, right? So it's you have 26 bits because the total is 32. So it's 6 plus 26, 32, right? And so 2 instructions, jump and link, can jump anywhere in the program segment, right? Anywhere in the text and memory. This is, again, for jump and link, it's kind of justified because you say the function can be anywhere, really, like they might be semantically related, but really how the compiler placed them in memory, the distance doesn't matter, right? So that's why it makes sense to jump as far as you can, right? Agree with this? So, and for that, they came up with this newer J-type encoding, which allows you to put 26 bits, and they play the same trick. They don't put the 2 zeros here, which allows you to essentially extend it from 2 to the power 26 to 2 to the power 28, right? And that will allow you to jump pretty far away. So it's something around, what's the deal here? Like, again, let's go to Python real quick to just verify the power here. 2 to the power 28 it's 206 megabytes. So it's 256 megabytes. So if I split by 3 like that, right? So it's a reasonably big program. So sorry for everyone who is like far away. So I just double check that. That's the address. It's an address range from 0 to 268 megabytes, right? So this probably works in most cases, right? Again, you can come up with a case when probably you kind of will be screwed, right? And what do they do here with the target axis? I'm not sure what this means. It's still relative to the PC. Like, this is the trick. So they take the upper bits of the program counter and essentially do an OR with this address. Or what kind of, oh no, and it's not an OR, I'm sorry. So they just take the upper bits of the program counters. Those bits come from the program counter, and then those lower bits come from the address, right? Which is a form which allows you to jump relative to the PC. So if you're loaded somewhere in, not in the lowest 256 megabytes, but let's assume at 1 gigabyte, right? So then you can jump in the like neighborhood of that 250 of the 1 megabyte plus 256, right? So, and they delegate this job to the linker, which we will cover. So you have to be careful. So this is where it gets a little ugly, right? So I agree that it's ugly, right? So that's their workaround. They say that you can jump around if you're suddenly trying to jump from megabyte 1 to megabyte 3, gigabyte 1 to gigabyte 3, then you kind of screwed and you have to do something else. And I'll show you in a second. Okay.
Just not clear so the last 2 zeros that are being left off is because we're multiplying by 4.
Yeah, but the intuition is that in memory, the program is always in the increments of 4. If this is individual instructions, each of them takes 4 bytes. And then if you can make an agreement that you load the program originally at the 4-byte offset, right? Then you always, no matter where you jump, maybe you jump somewhere over here, but the lowest 2 bits of the address will always be 0, right? Because it's the alignment. That's how it works in this system, right? It will be, it's like in decimal, if it's like alignment by 10, the lowest digit will be 0 always, right? Right, so it's the same in binary. So, okay, cool. So this is clear. So that's this is where it gets obscure, and I agree with you. Okay, like it was so beautiful and so not ugly up until now, and now it's like, yeah, you know, like taking upper bits from the program counter, adding bits, like erasing the rest of the bits. Yeah, a little ugly. And if you really have to branch to any of the addresses, right? So what will you do? What's the trick which you can guess? Yeah.
Can you like hide another branch or the dash so you branch to that event and then branch again?
Kind of, correct. It would be crazy to jump, you know, in gigabytes 1, 2, 3, 4 in increments of 256. But the trick which you can do is this. You can use I mean, that's not really the trick which I wanted, but it's a semi trick. So essentially, it's essentially like this. So if you want to jump further away, right, you do a short branch which jumps over this branch. J allows you to jump 256 megabytes, right? So that's the trick. So you cannot write it like this because L1 is far away, right? So you cannot write it as a single instruction. So you have to generate a sequence like that. So you say, look, if I want to branch to that long branch, then just don't branch over this one. So you have to change negate the condition under on which you jump, right? And this will allow you to jump to 256. If you really want to jump anywhere in the address space, remember you can do jump through a register, right? So we only seen it when the function returns, right? And I forgot JR or JA? JA or JAR? I forget how they call this instruction. And this one takes a register. So typically we were putting register RA, but you can actually put any register here, right? And then what you will do is that I said effectively, instead of this J, you will load a constant into a register and then jump through this register. So for example, you can use T0 as well and just jump to T0. And if it's a big constant at the very end of the address space, then you will have to use this trick with load upper immediate to make sure that you can compose the constant with the 2 different instructions, with a lower part and a higher part. Got it? Okay, that's the trick. So now we know all the jumps, and now the book will happily feed you this figure, which is for anyone who is, it's a little hard to decipher. And my trick, so let me just explain you what they mean by this figure, and then I will give you a hint on how to use it in such a manner that it makes sense. So they say, okay, this hardware supports the following modes of addressing. So immediate means that if it's a branch on equal, register R1, R2, and then immediate value, whatever the offset is, right? So we'll jump to this address, right? I disagree with this actually, with my example here, because branches, as we know, jump. This is a C relative address is a branch, right? So that's my example of branch when equal falls into this category. So immediate addressing, what's the instruction here? Who can tell me? I mean, I honestly don't know myself. So let's just look at it. No, but something is happening. So maybe there, it's more like a load. I would say it's more like a load or store, load a word or store a word, which allows you to say, look, use this register as an address RT. Okay, this is a mystery. Forget about it for a sec. Register addressing is when you essentially say something will will be happening in a register. So this RS is just a number of a register, like, right? And this is the value is in the register, not in immediate is probably when you put a constant inside. Okay, this is what they mean. Okay, got it. So it's something like the example here will be something like or immediate, right? When you say like take a register R1, R2, and or with some value 55, for example, right? So that's immediate value 55 is right here in the instruction itself. This one, you use a register number to point to one of the registers. Maybe it's like register like 7, for example, right? Number 7, and you pick the value from register, right? This one is the base addressing, where you say you take a value from a register, which supposedly should be pointed by this one, right? So this is kind of like a load and store instruction. Take this address and you add them together. Remember, load and store takes an offset, and then you go to memory, and you can either load the whole word, or you can load the byte, or you can load the half word, right? So we talked about it today. PC relative addressing is the example of this branch. When equal, for example, you say it's relative to the program counter. You take the address from the instruction and you add it to the PC. Remember that here you multiply by 4 and you go to the word in memory, right? Something like that. And then pseudo direct addressing is like in this jump instructions, where you're essentially saying, okay, I will take bits, those higher bits from the PC, would appreciate a better figure here. The address here, and you do this concatenation operation, and then you go to memory, right? But however, this is a little bit cryptic, and I totally agree with you that it's cryptic, but what's not cryptic is this wonderful table. So I will zoom in into part of it, so don't freak out immediately. But the beauty of this table, which is kind of like existential in a way, that almost the entire assembly fits on one screen. This is like unbelievable. So imagine everything what you write, like all these GUI applications can be implemented with those instructions, right? That's kind of cool. And how to use this table, you can always go and like check what's going on, but the table is very carefully constructed. So what they say here is that, look, if you use, for example, 20 here in this add immediate instruction, right? So this is literally S2 plus 20, right? So this is the immediate addressing, right? And so you immediately know how this instruction operates. If you say we see a 20 here in the load word instruction, you see again, it's S2 plus 20. No conversions, no multiplication by 4, it just plus 20, right? So, and it's a good fuzzy feeling, right? We didn't cover this one store condition that we will cover next time because it's relative to synchronization, but this is like first half of the table, everything is nice. Load upper immediate, you take 20 here, and you multiply it by 2 to the power 16. So roughly speaking, you shift it by 16 into the upper thing, right? So it's, again, it's a very good example. So like, no matter what question you have, always go to this table and it will give you an answer. And the second part of this table, it covers those, like esoteric examples where, for example, branch or not equal, and you say the number is 25. But in practice, you jump to PC plus 4 plus 100. So I explained how the 100 comes about. So it's 25 multiplied by 4, right? It's a shift by 2 because we don't store those zeros. I actually forgot to tell you that it's relative not to the current PC, but to the PC of the next instruction, right? So that's why it's PC plus 4, right? Is it clear? So it's a very concise reminder of what everything means. If you like get the gist of what's going on, then you understand it. So like it's again 25, so PC plus 4. So you take any instruction like branch when equal, branch when only not equal, stuff like that, right? Go ahead, question.
That's the program counter before you executed the branch on equal.
Right. So PC points, for example, to branch not equal here. And PC plus 4 will be pointing to the next instruction here. And that's what they use this one relative to this one. What's the real, why is that? Again, when we get to the implementation, I would guess that the hardware by default always compute PC+4, and that just keeps it around and it's easy. And then you can do some modification, do another addition on this one. But this is like always done, because a typical case is always do PC+4, right? And so it's the logic, the silicon which implements it is always there. So here's another good example. So for the jump instruction here, you say, I will jump to an address 2500, but in practice you go to 10,000, right? Because you multiply this address by 4, right? But it's an absolute address, right? If you do JR, this is what I was confused JA versus JR, jump through a register, then you go to the value of that register array, right? Or whatever the register can be, T0 as well here. And yeah, that's what I was trying to explain, that and the reason for that is that it doesn't make sense to keep 2 zeros around, because if you're jumping at the instruction boundary and instructions are 4-byte aligned, no matter to which address you jump, the lowest 2 bits will always be 0. And you make this observation, you say, why would I keep always 2 zeros? I know that there will be always 2 zeros, right? So just don't keep them, just extend the number with 2 zeros. And this extension, which is shift by 2, is multiplication by 4, right? Nope. Jump register just jumps to a value in the register, because the register itself is 32 bits, and you can jump anywhere in the address space from 0 to 4 gigabytes, which is 2 to the power 32. Agree? So, and this jump and link instruction, same deal. So relative jump relative to the PC+4, but again, since you extend 2 bits, instead of jumping to 2500, you're jumping to 10,000, right? So again, it's a little bit like, if you try to remember, I would say, forget about it. Just get the gist of it. And it kind of logically flows from the semantics of the instruction. So you say, you know, branch equal, I only have 16 bytes. So that's why, you know, I will just multiply this number by 4, but again, not relative to the program counter. So because branches are in the neighborhood of a current program counter, right? And so if we get this, like, this is, I mean, this is a table from the book, right? So, I mean, I didn't want to quote the number, but if you look for this header, MIPS assembly language, and maybe the number is different between the 2 editions, which we're using, 5th and 6th, right? But this is a useful thing. So an entire assembly, it fits on one screen. So when you write your programs, just go ahead and look at this table. And here is like a more concrete example where we have this loop label, right? The question is like, how do we encode these instructions, right? And again, there will be an assignment on encoding instructions. And this is an opcode, which is 0, right? Another opcode, which is 0. This one opcode is 35, branch not equal, opcode is 5, add immediate opcode is 8, and the book has a table for all the opcodes. Jump is opcode number 2. But again, so if you jump into the loop, right? It's a direct jump, and it allows you to jump to a specific address, right? So it's so we go to this table, we verify that this is an address, but multiplied by 4, right? And so the encoding will be, if you're jumping, and this one, it's an address 80000, right? Or 80,000 in decimal, right? So then the number which you will put in this inside the instruction is 20,000, because it will be multiplied by 4, right? So, and for another jump, which is here, branch not equal, we again go back to this table, check on what branch not equal is doing. Branch not equal is going to the PC+4 plus the number, but you encode it as the one which is divided by 4. So you say branch then equal is at the location 80012 plus 4 is 80016. And if you want to jump to to where you want to jump to exit, right? So you jump into exit, which is to address 80024, right? So the distance between them is only what is that? 24 minus 16. The distance is 8, right? So divide 8 by 4, you get 2, right? That's why you place 2 in this position, right? Is that clear? So, I mean, a little bit cumbersome, but kind of mechanical. So if you know how to use the table, you will be fine essentially deciphering and encoding the programs as well, right? Okay, good. Again, just a little bit of recap for the registers. Again, all the registers, or almost all the registers, there is just a couple of them left, are on this screen. So there is a special register 0, which has register number 0. And it always provides you a constant value of 0, right? And you don't do anything when you call or return from a function, you don't preserve it, right? Because you can't even modify it. So registers V0 through V1, what are those used for? But it says here, values essentially. So essentially, this is how you return results from a function, right? In these 2 registers, numbers 2 and 3. Preserved in a call? No. Argument registers A0 through A3. Preserved in a call? No. So you can use them as temporary registers inside a function, right? Temporary registers T0 through T7, numbers 8 through 15. Again, no need to preserve. Saved registers S0 through S7, numbers 16 through 23. They saved on a call. So the callee has to save them. Temporary registers T8 through T9. So they give us a couple more temporary registers here. Again, you don't have to preserve them. GP, global pointer, which points to the data section, right? And we'll come back to the data section again, so it will become your good friend. But essentially, what kind of variables are there in the data section? Who remembers? Static variables. Yeah, exactly. Stack pointer points to the stack. Global pointer, you have to preserve it. Like, it's kind of funny that you can override it, right? So in the user space, stack pointer, you also can override it, but it's natural. So which variables are sitting here on a stack pointer? Local variables, like the ones which are allocated in a function local scope, right? Frame pointer, I did not cover it. I can come back to it. It's just, I would say it's a waste. On modern machines, it's a waste of a pointer. So I don't think modern compilers can compile the frame in most cases. And array is the return address. So FP has to be preserved. RA has to be preserved and along with the stack on the indication, right? Okay, so we know all the registers, we know all the assembly, right? So that's a good point. So we know a fair amount. So again, we can write programs. And we still have 10 minutes and everyone has to go. Say this again. Okay, tell us why. So what do you think is lost? Why you're lost? So I'm actually following the book. So how many people feel like they are lost? Let's do a quick count, hands. So roughly 30%, maybe 25% of the class. What do you think will help you to be less lost?
Reading the book before class is good.
Reading the book is helpful, and I'm actually following the book, and I on purpose like bring the tables from the book so it kind of makes a connection with the book, so you can look back and like it's not just abstract, black letter, but it's really from a book. So what else?
I think if you put like the specific like parts of the chapter we can read in short class that were like in a chunker, that would be really helpful.
I actually follow almost sequentially the book, right? So it's very easy to kind of, when we start a chapter, just start reading, and if you look at the class schedule, you can guess upfront a little bit where I will stop. I don't say that you can guess, obviously. I often don't know myself because even now I was actually planning to cover a little bit more, but I would rather stop and talk. But you're right. So wait, so the conclusion is, okay, so there is a little bit of, I mean, I don't know what kind of classes you've been before. So this covers a lot. It's kind of like top to bottom from the machine. I try to be like in the last couple of weeks, I try to be kind of slow and consistent. So everything is like has a slide and a diagram. So, but still, like for me, it's kind of hard to improve it. So I don't really know what's missing. So maybe read the book. I kind of believe that I try to teach to like a 12-year-old. So in a 12-year-old, if you follow the class and you remember what was done before, even if you read the book after, I kind of say that you should be able to follow. And this is how the book is written. So we can do an experiment. I don't know, but I read the book and I just enjoy it a lot because of how simple it is in many cases. But okay, go ahead.
I'm just wondering, I've been following us to both until this class, just because I had a lot of other stuff to do, and I tried finding exactly which section we're covering. What we're
Mhm.
doing, or something.
Mhm.
So what sections is this material from this selection?
I don't remember the numbers, but you can easily map them. Yeah. So I skipped a couple. So I skipped the frame pointers. I skipped synchronization because it's a hard topic. So we have to cover it in a separate lecture. No, I agree. So sometimes when you read the book, you can run into a section which kind of kills you. It kills me as well. So just there is like even these tables, which the book has a better table, which I mean, I deciphered, but there is the book has a table with iteration encoding.
Have the library or the bookstore.
I didn't. Yeah. Okay, so any other suggestions? So wait, let's listen for 5 more minutes because it's beneficial for those 25 to 30% who are lost. Yeah, go ahead. No, we'll release it right now in a second. I just wanted to finish all the MIPS assembly because I wanted to assign kind of everything, and then you can start working. Yeah, I will adjust like to like Wednesday or something. Yeah, like you will have a week, so like there is no need to. The whole homework is to help you to learn, not to like punish you for anything. Yeah, any other suggestions? But okay, this is kind of still high level, and I kind of can dismiss almost all of what you suggest, saying I already done it. But the question is like, how can I really help? I can slow down even more, but then we will have to drop some chapters. What's the solution here?
You do like a practice problem posted on campus. That's going to be like practice like problem homework. So we have an example.
But why do you want to work on it twice? Just work on the homework. The homework is not to.
I just want like the examples from.
Like you solve it.
Yeah,
Like-
So you just post something, you pose the question.
And
you post
solve
your
it.
solution.
It's just nice to have.
Okay, got it. So for the homework, example solution, got it. But got it. Yeah, that's a good idea. So when I will be typing the homework, I will provide like a couple of sample solutions on. Yeah, and I did it, I think, in the first one when it was very obscure. I said, okay, I expect the answer, which looks like something, but there was some other thing. Yeah. What pages? Like it's chapter 2. It's and there is an appendix, but I'm not covering appendix. So just it's all chapter 2 right here. Like the book is there. So people who are lost, again, one other suggestion from me, like we have 4 TAs and I have office hours and I'm always happy to talk to you. Mine are right now at 1:30. I'll grab a quick lunch. I will be there in my office. It's a temporary office, but I updated my web page and I think Canvas. I would say use this chance to talk to me. There is no, I mean, I'm not going to judge you. Like if you come and ask a stupid question, I will be there to answer. And TAs are there. I mean, I was in this position. So last year I took a class in which I was like you. I wasn't able to type a line of code. It was Daphne tier improver. Just simply didn't know the syntax. I learned the syntax by week number 2. But then I was still lost in the theorems. I wasn't able to, but there were like 3 TAs. I was bugging them as much as I could. I learned something, not everything. So, but that's the way to learn. Just use your TAs as much as you can. And someone was saying adjust the TA hours if it's a real issue. But just give me a sec, guys. No need to run. I have 1 second. Look like this. The red one is still 1 minute, half minute. If there is a need to adjust the office hours, like on Tuesday and Thursday, people were saying, okay, they overlap with some other class. So raise a concern on Piazza and we will move them. So to make sure that you can attend. So, but book TAs are the best things to do. I kind of explained the book in the lecture. So whichever you prefer, lecture first or book first. When I was a kid, I didn't read the book. I was lecture and then the book. I wasn't able to understand the book either when I was young. Now it looks easy to me. Okay, thank you. So I'm done. Which one?
No.